A pleasant day to you all. Today I am excited to delve into a fascinating intersection of gaming and artificial intelligence by exploring the game of 2048 and how we can enhance our gameplay using the Minimax algorithm. What is 2048? It is a single player puzzle game where the objective is to slide numbered tiles on a grid to combine them and create a tile with their number 2048, right? Just like what you're seeing from your left side. It's a game that challenges both strategy and foresight. So why did I choose Minimax algorithm? Minimax algorithm is a decision-making tool commonly used in game theory and artificial intelligence. It helps determine the optimal move by minimizing the possible risks in a worst-case scenario. In the context of 2048, this means evaluating potential moves and predicting future states of the game to maximize the chances of reaching the 2048 tile. So, in this presentation, I'm going to give you an overview of 2048 game mechanics, then the principle of Minimax algorithm, then how to implement Minimax in 2048 game. So, this 2048 game is played on a 4x4 grid like this on your left side, and each cell can hold one tile. Each tile is power of 2, like from 2, 4, 8, 1632 up to 2042, which is the final state. And the game starts with 2 tiles, usually one tile with 2 and another with a 2 or 4. So the players can slide the tiles in 4 directions, either up, down, left or right. When 2 tiles of the same number collide while sliding, they merge into one with the sum of their values. For example, if you are to combine a tile with number 2 and another one with number 2, they're going to form a single tile with 4. So the game is won when a tile with the number 2048 is created. The game ends when there are no valid moves left, meaning no empty spaces and no adjacent tiles with the same number. For example, this grid is showing us that there are no more empty spaces. And then if you are to move onto this one, we can still see that we still have empty spaces, so the game is not yet over. So this Minimax algorithm works like this. The algorithm recursively evaluates each possible move and its outcomes. So we are going to have a maximizing player and a minimizing player. So a maximizing player is going to choose a move that is going to maximize their score, while a minimizing player is going to choose a move that is going to minimize the maximizing player's score. So now, how does this Minimax algorithm works? Right, you have to generate a game tree like this one that you're seeing from your left side, right? And then in this tree, this root node is going to show you the starting state of the game, and all these nodes, they're going to show you the initial states of the game. And these edges, they're showing you all the possible moves that you can do. So how does this Minimax works in 2048 game? It can evaluate potential moves by simulating possible future states of the game. It also assesses the outcomes of merging tiles and the resulting configurations, allowing players to make informed decisions. By maximizing the likelihood of reaching higher numbered tiles while minimizing the risk of running out of moves, players can achieve better scores. So, yeah, this prologue code implements the Minimax algorithm for the game 2048, focusing on shifting and merging tiles, evaluating board states, and determining the best move. So let's break down the code step by step, starting by the first part. Shift and merge a row leftwards. So this predicate, this one, shifts and merges each row of the game board to the left. The first clause, this first clause, handles the empty list case, returning an empty list. For each row in the board, it merges the row leftwards using merge left and recursively processes the remaining rows. Moving on to the next predicate, this one, merge tiles in a row while shifting left. This exclude is equals to 0, removes all 0 tiles from the row. Then this merge pairs merges adjacent tiles that have the same value. It also calculates how many zeros need to be added back to the end of merged row to maintain a length of 4. The merged tiles and zeros are appended to form the final shifted row. Moving on to the next predicate, merging of adjacent tiles. The first clauses, those first two clauses, handle empty list and single elements. So if two adjacent tiles are equal, they are merged into one tile with double the value. If they're different, the first tile is retained and the process continues with the next tile. Now we are moving on to the next predicate, reverse rows of for right move. So this predicate reverses the rows of the board, which is useful for implementing right moves. It reverses each row and recursively processes the rest of the body. Then moving on to the next predicate, it initiates the Minimax algorithm for the maximizing player. This Minimax algorithm predicate, right? It generates all possible moves from the current board state using find all. Then best move 5 is used to determine the best move based on the current board and available moves. Moving on to the next predicate, right? We're saying if there are no moves left, it retains none as the best move here, right? For each possible move, it applies the move to get a new board state. Moving on here, this evaluate board evaluates the new board. If the score of the new board is better than the best score found so far, it updates the best move and the best score. Then this evaluate board evaluation function, sum of board values. The function evaluates the board by calculating the sum of all tile values. It flattens the 2D board into a 1D list of computers and computes the sum, which serves as a basic evaluation metric. Then the last predicate starts the game by initializing the board and invoking the Minimax algorithm. It sets the depth of the Minimax sage to 3, meaning it will look ahead 3 moves. Finally, it prints the best move determined by the algorithm.